You're saying poor Boyle is buried in London when you asked Google.
Yeah.
In Westminster. Yeah.
That's not what I was told. Yeah. Somebody's lying. All right. We'll continue. Next lesson's not so difficult. All right, hang on. Ba-ba-bum. Where is Boyle? Robert Boyle buried. No. This is Who is buried at Saint? There's somebody buried at that cathedral, I know.
Over 500 people.
Yeah. Let's see if any of them are famous. Well, maybe it wasn't Boyle. Maybe it was somebody else. I thought it was Boyle. Michael Boyle. What's it like? His brother nobody heard about or something. Oh man, I'm so disappointed.
Why did you
None of these. Jonathan Swift's a famous author. I'm heartbroken. I really am heartbroken. Because somebody who went on the tour said Boyle is buried here, and I assumed they were talking about Robert Boyle, the physicist, but it looks like they're talking about this Michael Boyle. Heartbreaking. All right. Okay, so I have to stop telling students that. So, okay, Ohm's law and IV graphs. Now, I should tell you that this lecture is very, very important for your labs, because next semester you're going to do 4 labs, and one of the labs is about this topic. And this is the topic. Okay, so let me just take it one step back. Next semester you have to do 4 labs, okay? 3 of the labs are just handwritten reports in a notebook. But one of the labs, the special lab, is worth 10%, and you have to type it up as a report. You know, fairly big report. And the lab is this one. So this is important for your lab. This is worth 10% next semester. Okay? So
4 in physics.
4 in physics, 3 are handwritten, and 1 is typed for submission.
Handwritten?
Which one?
Like by handwritten, like.
Yeah, just like in a notebook. Yeah, but one of them you type and submit. Okay, continuing. Ohm's law and IV graphs. Okay. Here is a very simple circuit. Now, this circuit is very important circuit. It comes up in the exam from time to time, and this is the circuit which you'll need for your lab. In the lab, I don't actually tell you how to assemble the circuit. It's your own sort of lab. So you have to research how to do this yourself. Of course, you can go to books and go online, but I mean you have the notes from your class as well. This circuit is it's simple, but it's very important. So first I'll let you draw the circuit, and then we'll talk about what happens. You drew that? I think the other two drawn. What class did you have this morning? Maths. So what did you do this morning? What topic?
The volume derivative.
You mean the optimization? Yeah. And you finished that?
No.
You did some of it? Yeah. It's tough, isn't it?
Okay.
The word problems. Yeah. Okay, you have that drawn? Yeah. Alright. So look, let's imagine that this battery, we'll just imagine for example it's 10 volts. 10 volts. Now, if I set this to 0, then the voltage here all goes into the resistor here. So what would the voltmeter say here? It would measure out 10, because everything here went into that if you make this 0. So it gets all the voltage. Now, let's say we turn this up a little bit. So there will be a little reading on the voltmeter here. But this voltage plus this voltage has to still equal 10. So if I increase this so it consumes 1 volt, then what will this voltmeter read? 9 volts. If I increase this so that it consumes 2 volts, then what will this read? 8. So the purpose of the variable resistor here is actually to change the voltage here. Because if this uses more of the 10 volts, then this has less. Is that okay? Or, think about it like if I can take stuff there for a second. So let's say this is a big light, and this is a light that I can adjust. Okay, and here's my power. Say it's 10 volts. If I have this to 0, then all 10 volts go into making this light shine. If I start to turn this light up, what would happen to this light? Well, it'll start to reduce, get dim, because this is still fixed. It can only provide 10 volts. So the purpose of the variable resistor is actually to change the voltage this receives by having this take some of the voltage first. Do you understand the purpose of it? So this circuit here is quite interesting, because what you can do is you can adjust this and you can see the V change, and you can see how the A changes the current. So this is a way to discover the relationship between voltage and current for this resistor. So let's have a look at some data, for example. Okay, so in this example here, I had 10 volts. So at the beginning, the 10 volts is because I probably had this set to 0. As I increase this, what happens to the voltage? Decreases. So can you see? It goes from 10, and I have it to go down to 1. What happens to the current? As the voltage is decreasing, what is happening to the current? You see it's also decreasing. What is very interesting is the graph. Let's plot this data. And this graph is very, very important graph in electricity. So I'll give you. You don't have to be very neat. Okay, I'll just give you a minute to plot this. But first, you should copy this table. And yeah, sorry, I'm just going to open up a graphing program here.
Which one goes into the x-axis?
Oh, good. Usually the thing that you change goes on the X. So what do you think it is here?
Voltage?
Yeah. And then the thing that you measure in response goes on the Y.
So V is at a y-axis.
No, the other way. Because V is the thing you change, you put on the X. Then the current is what you measure, its response that goes on the Y. You've got that? We can draw it together. I'll be a lazy pig and have this program do it for me. Let's see, voltage in volts, current in amps. And we start off with 10 volts, correct? And do we decrease by 1?
Yep.
Until we get to 1 volt. And then the current starts at 20 and it decreases in 2s, is it? Right, let's draw this. Insert chart. Whoa. Scatter. That's fine. That's fine. Oops. node IV plot voltage in volts, current in amps, and away we go. So you all should have a graph that looks like this, I hope. Let me shrink it down a little bit. And move him. How do I move you? Come on. There we go. And actually we can connect these up, but I won't. You could draw a straight line. It's obviously linear. Okay. This is called the IV characteristic curve, the IV plot. It's like I said, it's very, very important because it tells us behavior of the resistor. The IV characteristics of a resistor is the plot of the current running through it against the voltage around it when the power source provides a varying voltage. So basically it's the plot we just made using the circuit we just had. It's called the IV characteristics. Now the reason it's important is because different resistors produce different graphs for different behavior, which we'll talk about in a moment once you write this down. Got that? Yeah? See that? Yeah. Okay, so look, why do we care? Here's an example. VI/OR. What does OR equal? That's V over I. Okay? Now if you look at your graph here, this is I and this is V. This is V. So what's the slope? The slope would be I over V. So here the OR is equal to V over I, so it means it's equal to 1 over the slope. So in other words, a big slope would mean a small OR. So when the graph is steep, when the graph is level, a small slope would mean a big OR. So in this graph here, the slope of it represents the resistance. Sorry, the slope of it represents 1 over the resistance. Now, this is linear, and actually that's a law. It's called Ohm's law, and Ohm's law states that for some materials at low voltage and low current and a constant temperature, the graph will be linear. So this here is an example of Ohm's law. If the voltage and the current is small and the temperature is constant, then for some materials the graph will be linear, passing through the origin, which is exactly what you have here. Okay, this is Ohm's law. Now I should give you a warning. Some people mistakenly think this is Ohm's law. That's not Ohm's law. That's not Ohm's law. That's not Ohm's law. Ohm's law is this. Okay. Now, some of your physics books might tell you Ohm's law is this or that, and a lot of them shockingly are wrong about it. And I understand why they're wrong, because it's high school physics and they want to keep it simple. But this is Ohm's law.
I did a presentation.
Hmm?
I did a presentation and I talked about Ohm's law.
Yeah.
I used the equation.
Yeah. But don't worry, none of the teachers noticed. Who was watching you?
Connor.
Ah, yeah. This is shocking news to you, is it? No. What did you use as your source? Wikipedia. You got this? Now this is actually, no, all respect to Mr. Ohm here, but this is actually a pretty bad law, because it's not even something that's always true. He only said, for some materials, at low voltage and low current in constant temperature, the graph will be linear. It's really not a good law. Like, at least with Newton's law, you can say F always equals ma, or kinetic energy is always equal to half mv squared. Whereas Ohm's law is like, add some materials, and it's for some voltage and some current and some temperature. Yeah, it'll be linear, I guess. So, it's not exactly the best law in physics. And it's not even always true. Sometimes it's false. If it actually is true, then we describe the material as being ohmic. And if it's not true, we say it's not ohmic. So, here, because this obeys Ohm's law, we call this resistor ohmic. If we didn't have a straight line, we would call the resistor non-ohmic, because it doesn't obey Ohm's law. But I don't like using the word law, because law means it's something you always have to obey. So maybe like Ohm's rule or something, I don't know. So you need this terminology ohmic. Got that? Yeah? And we looked at what the slope represents already. Represents 1 over the resistance. So what's the unit of the slope? Well, if it represents 1 over R, then it's 1 over ohm. And we talked about this, but I think it's worth writing down. The slope is 1 over R. So if you don't have that written down, you need to write that down. Because you can use this to calculate the R. Because the R will be 1 over the slope. Now you remember I said we don't use ohm meters to measure resistance. In fact, we use this to measure resistance, this graph. Okay, continue. Now, let's have a look at this, but let's do it together. So, my values change a little bit here. So the current instead will be 14, 13.5, 13, 12, 11, 8, 6, 4, 2. What's gone wrong?
11, 10.
I missed a 10. Flip. 10, 8, 6, 4, 2. Right. Now, look at this graph. Would you say it's a straight line? No, definitely not. At the beginning, it's steeper than at the end. So the slope is reducing. So what does that mean about the resistance? Increasing. So you get more resistance at the higher voltage than at the lower voltage. So is this material ohmic? No, it's not. Let's have a look at the questions I asked you to do here. So the first thing I ask you to draw the circuit. Fine, you have that already, the circuit at the beginning. Okay? Use the table below, draw the curve. Fine, there it is there. Okay? Now, so what I want you to do, just quickly sketch it. The most important thing is that you get the shape, that it goes straight and then it curves off. Don't worry about being so accurate with the numbers, because I have it here. Now, before continuing, an important point to make. So, you know in your distance, speed, time triangle, how would you calculate the time? Distance over speed, okay. So suppose I say, Andek walks to the train station, and he walks at 5 kilometres per hour, and the train station is 3 kilometres away. Could you work out the time? You could, because you have the two. Now suppose I say, okay, Siva walks at 4 kilometres per hour to the train station. Could you work out the time? After I told you about Andek. Yeah, because do you know her speed? You do. And do you know the distance? You do. Kind of, though. Because you don't actually know if she travels the same way that he did. It's probably the same, right? That's the same thing that's happening here, okay? You can have different voltage and different current, and yeah, most of the time it gives you the same slope, the same resistance. But then in some situations, a different voltage and a different current gives you a different resistance. A bit like with walking to the train station, you know. Yeah, if he walks with one speed and she walks at the same speed, yeah, it's probably going to be the same time, because the distance is probably the same. But you know, maybe not. Maybe she walks a different route, so the time is not what you expect. That's the same thing that's happening here. Okay, the resistance is usually a constant. The slope is usually constant, but not always. Not always. Okay, so let's continue. The next part is calculate the resistance. So resistance in ohms, V, I, or is V over I. So I just do V divided by I here. Wait, I did that upside down, didn't I? V, I, or is V over I. No, I have it right. Do I? Yeah, no, I do. Sorry. I do this every year. Yeah, no, that's right. Okay, so as the voltage is increasing, what's happening to the resistance? It's increasing as well in this one here. Can you see the voltage goes from 1 to 10, and the resistance goes from half an ohm to 0.7 of an ohm. Now, if I was to delete this part of my data, you would describe the resistor as ohmic, because it has a constant slope and constant resistance. But if I include this part, would you describe it as ohmic? No. And that's what Ohm said. Only for some voltages and currents is it ohmic. What is the smallest and largest resistance? It goes from 0.5 up to 0.7. And finally, is this material ohmic? And the answer is no. Okay. This is okay? We can continue? Yeah. Will it matter if we run the current backwards? Well, most of the time it doesn't. So like for example here, here, sorry, I'm trouble drawing straight lines. There's the voltage and there's the current. And there's our ohmic material. If I take the resistor and turn it around, or if I just turn the battery around, the values will become negative. If everything is swapped, you'll get negative current and negative voltage. But you kind of picture, well, it doesn't really matter, it'll just be the same in the opposite direction, you know. That's the same for a lot of things. Like in this graph here, if I was to swap it around, you know, it goes like this. So over here would, let me try and draw that little bar. It levels off here and it levels off here. It'll be the same. Well, for the simple resistor, yes. Oh, I forgot to tell you what this represents. So this behavior happens with things like light bulbs. If you increase the voltage in a light bulb, it produces more resistance because it starts to overheat. Okay, so this is an example of a light bulb. My previous one is an example of just a simple small resistor. And in both cases, the graph is the same in the negative and the positive. Okay, but you get something interesting with the diode. With the LED light, remember I said it prefers the current to be one direction. It doesn't like the current going backwards. So if I have the picture here, yeah, let me explain this here. Firstly, there's two interesting things about the LED diode. The first thing is, as the voltage increases, what happens to the slope here? Does it become steeper or less steep? Steeper. So what's happening to the resistance? Decreases. This is the opposite to those lights. Okay? With those lights, as you increase the voltage, you get more resistance. But with the LEDs, like you know, the LEDs on your phone. Oh, I left this on. The LEDs on your phone, they get less resistance as you increase the voltage. That's actually very useful because it means it doesn't overheat, which is why you use it. But look what happens when you try to put the current backwards. So this is the second interesting thing about it. The slope here is quite flat. What does that make the resistance? Yeah, well, I mean, does it make it big or small? What do you think?
Zero.
Well, the slope here is zero, right? Or nearly zero. So what's the resistance?
Very big.
Very big. Very, very big. In fact, it's so big, it doesn't let the current pass through it. If this is zero, then the resistance is infinite. You know, 1 over 0. So that means it blocks the current completely. But if you push and push and push and push the voltage, more and 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 more, eventually you'll break the diode and all the current runs through and you have no resistance now because it's very steep slope. Okay? So this point here is called the threshold. If you increase the voltage enough, you get no resistance. And this point here is called the breakdown. You broke the diode. You've increased the voltage so much that it just eventually breaks through. So this part and this part are not the same. You have a longer time to wait until you can get this. Okay, it's not symmetric in these opposite corners. Now, last year and the year before actually, they asked you to sketch the IV for a diode. Okay, so you have 3 that you've learned in this lesson. The first is the simple one, that's linear. The second one is the lamp, that's linear and then curves. And the third and final one is the diode, which is that. Oh, and lastly, they were total jerks as well in the exam last year, because not only did they ask you to draw it, they also asked you roughly what this voltage was, which I thought was being a total jerk. So just so you know, this is usually around about the 0.7 volts. Yeah. Although I think if you wrote down one vote, I might have given it to you. I thought it was a little unfair to ask that. Did you draw that? Have you got that? Yeah. So I'll just let you try. There's two questions, but there's only really one question. I give you some data and I ask you to make the plot and answer a couple of questions. So, that'll only take you 5 minutes, and then we'll finish. Okay. So if you can just try to do question 1 now, and then you can do question 2 at home. I was being a little bit sneaky with my units. What units am I using for current in the table? Milliamps. So if you prefer, you can change that into amps by just making it 0.5. That's what I would recommend. Can I close this? Yeah.